So we've seen that looking at the distribution shape can identify outliers, and that those outliers can be a problem. Other issues that can be observed by looking at the distribution are floor or ceiling effects. Floor or ceiling effects result in skewed distributions because of naturally occurring low or high points on the scale where most of the responses cluster. Income is one of these. Income for most people, I've mentioned this before, for most people tends toward the low tens of thousands, and of course 0 is a naturally occurring low point below which we can see no scale data points. But a few people will have very, very high incomes, and creating a distribution that's skewed to the right. Satisfaction with popular brands is another scale that may show a ceiling effect, where most people are very satisfied, and they will report that they're very satisfied by selecting points on the far right of the scale, and they can't go any higher than that. But there will be a few people who report being dissatisfied, and so there may be a tail that's skewed off to the left. Ordinarily, increasing the size of the scale does not help to create a normal distribution. If you have a 7-point satisfaction scale and most people are satisfied, then you're going to get a lot of responses that are 6 or 7. And if you try to reduce the skewness by giving people a 10-point scale or even a 50-point scale, you're still going to see the skewness. On a 10-point scale, instead of responding 6 and 7, most people will respond 9 and 10. And if you get them a 50-point scale, most people will respond from 45 to 50. Sometimes the problem can be addressed by changing the endpoint anchors. So giving them the same size scale, but describing the ends and making the end points seem extreme. So instead of saying very satisfied, the endpoint might be the most satisfied I've ever been. So a 7-point scale could run from the least satisfied I've ever been to the most satisfied I've ever been. And that may succeed in reducing that tendency to pick the very end points. The second issue that can be identified by looking at the distribution is bimodality. So this classic two-hump distribution where you sort of have what appears to be overlaid normal distributions. And you will see a high kurtosis statistic for a bimodal distribution. And often it does indicate that there are indeed two normal distributions being reported because there are two subgroups or two segments responding. And so what the researcher does when he finds this bimodality is try to understand it in terms of a category variable. Maybe it's men who are showing up on the low end and women who are showing up on the high end. Or maybe it's young people showing up on the low end and older people showing up on the high end. And if that category has been measured, then of course it can be statistically controlled. So those two segments can be separated, and then if that's the solution to the problem, then what the researcher will see is a normal distribution for each of the two subsegments. So here are two distributions that show skewness. So on the left we see a distribution set that's positively skewed with a mean of 2.9, but a number of scores out in 6 and 7. And you see the skewness statistic there is 0.59, a positive skewness. So that's a floor effect. It's called a floor effect because there's a floor at the 1-2 point below which people cannot score. And on the right side we see a ceiling effect where most of the scores are 6 and 7. The mean there is 5.3, and you see a negative skewness minus 0.70 indicating that the distribution is skewed to the left. And here we see a bimodal distribution. So the gray area represents the total sample, and you see that there seems to be a peak at about 50, and then there's another peak at between 60 and 70. And the dashed lines indicate two subgroups, one that captures that lower peak and one that is appropriate for the second peak. These are data for the preferred or expected price of a glass of wine at a restaurant. And the two subgroups are divide the sample by social status. So the lower social classes show the lower expected price per glass, and I think that scale is $4.50 is the mean of the lower status subsample, and $6.80 is the mean of the higher status subsample. And that makes sense. You would expect that higher status people would A, be more familiar with more expensive wines, and B, be willing to spend more on wines at a restaurant in order to reflect their sense of social position. A final comment about descriptive statistics is statistical inferencing. Statistical inferencing is drawing conclusions about a population parameters from sample information, the estimates we derive from samples. So most commonly, we are trying to describe a population the same way we have been describing samples here. We don't describe a population by listing every value in the population. We describe it by identifying the mean or average or median or mode and describing the amount of variance. And clearly the process of statistically inferring those is to use the sample estimates, the sample mean and the sample variance to talk about the population. The information content of samples is characterized by the standard error of the mean. Again, that standard error of the mean, designated as S sub x bar, is S, the sample standard deviation, divided by the square root of n, where n is the size of the sample. The standard error of the mean reflects the information value of the sample. It reflects the reliability of the sample. It I guess, inversely reflects reliability in that it's an indication of the error in that information, the error component in that information. So lower standard error of the mean means that the information in the sample is more reliable. And there are only two terms there, so you can see that the standard error of the mean increases with higher population variance, and it decreases with higher sample size. So to conclude this lecture on descriptive statistics, let's put the standard error of the mean to use and characterize our sample data, either the descriptive, which is in terms of the mean, or the frequencies in terms of proportions, and talk about the confidence with which we hold those sample estimates. So confidence intervals. Confidence interval, CI, about the mean can be computed as x bar, which is the sample mean, plus or minus z times the standard error of the mean, s over the square root of n. The confidence interval about a proportion is equal to p, the sample proportion we observe, plus or minus z times the standard error of the mean for proportions, which is the square root of pq over n. Now notice that, so what a confidence interval means that the researcher believes that the sample plus or minus some error component captures the population parameter at some level of certainty. And the level of certainty is reflected by the z-score. So the larger interval, you have a larger interval when you demand higher certainty. So if you want to be 99% certain that the interval captures the population parameter, then you're going to have a higher z-score in this equation. If you're willing to be only 80% certain, so you're willing to tolerate a 20% error rate, then you're going to have a much lower z-score. So that plus or minus component will be smaller. You also have a larger interval when the population variance is higher. That population variance is reflected in a higher sample variance, S, or a higher sample variance for proportion, which is the square root of PQ, higher sample standard deviation. And in both cases, you'll have a smaller interval with a higher sample size, a larger sample. In all cases, increasing sample size gives you more information, and that increase in information is reflected in a smaller confidence interval for the same level of certainty.